Thank you for coming to the talk. And I'd like to actually start with a quick demo. Let me see if you can see this. This is Vocoflex. It's a real-time voice transformation plugin we just released half a year ago. What it does is, might be quite scary. Let me just show you a sample. This sample is by one of folks at Dreamtonics, our colleague. If you watch our YouTube channel, you know this guy called Miguel, who does all the product demos. This is his singing voice.
Baby, you know that I've been trying, but I just keep running. I just keep running.
Okay, so what I'm gonna do, I'll open Vocoflex and then drag that particular recording, just 35 seconds, into Vocoflex. And you get a curve. So, okay, everyone listen up.
Never gonna give you up, never gonna let you down, never gonna run and desert you.
Okay, achievement, that's achievement. So we have this little bit of a powerful and dangerous toy here. You just putting anyone's voice and being able to replicate a timbre, and being able to do in real time in 35 millisecond latency. And also what you're hearing now is actually the voice being transformed and added a watermark to it. So we're adding the watermark to be able to trace who's using this plugin, who's creating all the content. So in the case of when we run into like an ethical problem, we're able to track who's using it and probably like revoke the license, or we can take some measures against it. So with that, let's start. So we're talking about audio watermarks. There are a couple of reasons for adding audio watermarks. So for a Vocoflex, we want to add watermarks as a deterrent to unlawful usage. And for all the practical software developers, it'll be good if you have some way to track if unfortunately you have any pirated copies. You want to make them traceable to know who's making these copies. And lastly, there are like emerging laws and the regulations when you're making generative AI-powered audio applications. You need to required by law to add a watermark to track who's using the software. There are existing ways of adding watermark to an audio. We're not talking about like just flipping the least significant bits, like hiding information there, right, or injecting noise into high frequencies where you can't hear it. These are just too basic. They're just simply too easy to bypass. We're also not talking about like watermark just for verifying if the audio is generated or not, because it's not trackable. It doesn't identify the user. So a lot of existing approaches talk about assume an online scenario where your audio processing and the watermarking system all run on the cloud. In that case, the whole system is just a black box, so you don't care really, like you don't worry about the possibility where the audio before the watermarks are added get leaked to the public. But in our case, if you want to have like a real-time effect, something it has to run offline to get that latency. And if you're talking about offline plugin, then it's always accessible to reverse engineering. So given experience, reverse engineer, it just takes a couple hours to find out what's going on inside a program and bypass the watermark. And then you're just as good as throwing on the software around without a watermark. So we want a powerful, robust, and secure method of adding watermarks offline. If you try to be a little bit vocal, a little bit clear on the requirements, first, we want the watermark to be unique, so each user gets a different watermark ID. We want it to be robust against common audio modifications or transformations, like uploading into YouTube and download it, and you still can extract the watermark, like noise, or if you talk about vocals, if you mix the vocal with the instrument, you still want to recover the watermark. Or as I'm doing this demo, the voice is being transmitted through the speaker, and if you record it on the phone, you'll still be able to extract the watermark. And program security, so enhance your program against crackers, so the watermark part cannot be bypassed. And lastly, being able to add watermarks without increasing the audio latency. So there's a lot of requirements. Fortunately, we have some starting point, and these are quite recent research. Just talking about how to add robust audio watermarks that can withstand transformation and compression. There are studies on using a neural network to embed watermarks into the speech or audio. So these approaches are being tested on like artificial or like in a real physical environment, and they've been shown to be pretty robust against some quite heavy noises. And I did some study, and in general, they can be generalized into this kind of paradigm where you have two parts of neural network. One is the one for adding the watermark to the audio. It's called embedder. The other one is you take the watermark audio and use that network to extract the watermark. And when you're training them, you train both networks together. So it's a little bit like a game. It's like an adversarial setting where one network is trying to defeat the other. And when you train them together, they end up producing a strong enough watermark that is inaudible to human ear, but it's still being pretty robust. Now, if you want to enhance it against audio modifications, it's actually pretty simple. All you need to do is when you're training it, you just intentionally add some quality degradation in the middle. So the networks, when they work together, know how to compensate for that degradation. So for that black box here, you can like add noise, you can do a low pass filtering, quantization, distortion, add EQ, reverb. As long as you implement the signal processing in a differentiable way, the network, you can propagate the gradient and train the network to generate some really strong watermarks. So just talk about robustness, that problem alone isn't challenging actually. What's challenging is even if you can train neural network adding watermarks, it is still a separate stage. So if you're doing the offline, you're still just as good at having no watermarking stage, because to a hacker, you can just virtually bypass it and get the audio before adding a watermark. So the direction here is we want to fuse the watermarking logic with the programming logic, make them into one big network, so there's no way to skip that part. And from here on, this is where this talk gets really interesting, because I don't think anyone has done a study or has published anything. So what you're seeing from now on is the first time I have reviewed this technique we have discovered to the world. So the first step is you want to fuse the watermark neural network into the audio processing neural network. It's actually pretty straightforward, just train the two together. Instead of training the watermark embedder to recover the a perceptually similar input audio, instead you just train to predict the target audio. So that's how you just combine the two network into one. And in the case you're not doing like a voice conversion, if you're doing vocal synthesis or text-to-speech, you just swap the input audio with like the MIDI or be the text and train together with the watermark extractor. To this point, it's still straightforward, and you get one giant network that does both audio generation and watermarking, making it not separable. But there is a caveat, because if you look at the right-hand side of the graph, there's still like the input watermark ID. The ID for the user has to be sent in the program from somewhere. And even for the hacker, even if you're not like taking off the watermarking neural network, you can still intercept the ID and just replace it by all zeros or ones. And you're still as good as having no watermark, because it's a damaged watermark. So if you look at what we've done, the natural step for next is to incorporate this watermark ID and take it inside the network. So make it one giant thing that has both audio generation, watermarking, and the ID itself. But in order to do that, you would have to produce one unique network for each of the users. So if you think about like from the service design perspective, we have the client side and server side. Even for an offline plugin, it's common that the first time you run a program, you have to enter like a license code or something. And that part goes through a server. So on the server side, once you verify the license, you can generate a watermark ID for that user and somehow generate a new neural network with the watermark ID embedded inside it and send it back to the client side. Now, the whole question is, how do we generate a neural network with the watermark ID? I mean, the naive way is like you just train a new network, but that's going to take hours and a lot of electricity bill. You can fine tune it, but it's still going to take some time. The most elegant way to think of it is you just train a neural network to generate a neural network. So we're talking about Hypernetwork here. the Hypernetwork takes a watermark ID and generates a whole bunch of weights, which is used to construct the actual audio processing plus watermark embedded neural network. And only the parts inside this box are sent back to the client side. Now, how to train this? Before we talk about that, let's first take a closer look at the Hypernetwork. In typical setup, you have this is one layer, fully connected layer for neural network. You have a matrix multiplication plus a vector and sent through a nonlinear function. The Hypernetwork difference is you take the double matrix and express it with a different neural network. So you literally you're generating a network with a neural network. And the way you train it is you don't train this directly because all the parameters are being generated by the Hypernetwork. Instead, in each training iteration, you generate a random user ID for each sample in the batch, and you use that to generate a new network for each sample in the batch. And the rest is the same. So you're just training a Hypernetwork to generate like networks that can generate watermarks. So the Hypernetwork approach does infuse like all parts inside the same network, but so far we have one assumption that is neural networks can be treated as a black box. So we're assuming that there's no way to modify network itself to rip it off like the audio watermarking feature. But there actually is a way to do it. It's called collusion attack. Collusion, not collation. So the collusion attack means there could be more than one malicious user that are colluding together. So each of them get a different neural network, and then they gather their network together, and you just take all the weights and take the average of all the networks they're getting. And since the way we're generating the watermarks are random, so there's a good chance that the average neural network are still somewhat usable. But now, because they're all averaged, obviously the watermarks are gone, are damaged. This is actually a classical problem. It exists before with even talking about neural network audio watermarks. So 2 decades ago, when CDs and DVDs are still a thing, publishers are trying to prevent users from making pirated copies of the music or DVDs by inserting watermarks into them. And back then, there were techniques designed for preventing this kind of collusion attack. One way to do it, a really cool way, is the anti-collusion code. That is, you can mathematically construct a list of IDs such that when you combine any up to K out of them, the combined ID can still be uniquely identified. If this sounds like fancy and unachievable, there's actually a toy example. If we're only concerned with 4 users, we can just literally just make all the bits 1 except 1, make them 0. Now, if you take the average of any 2 of them, you've got 2 1s and 2 0.5s, and just look at which base will become 0.5. You know whose code got mixed in that. But this is not a very scalable example because in order to support n users, you literally need n bits. If you're talking about like 1 million users, you need 1 million bits, which is not doable. But there are clearer ways to construct them. And it's quite a mouthful word, BIBDA and the ACC, offer protection using complexity of square root of n bits. So if you're working with 1 million users, you only need 1,000 bits to protect them. But that's still a lot of information. So we propose a different way of preventing collusion, that is anti-tamper training. So the idea here is if you ever try to damage the neural network, damage watermark in the neural network, we make it in such a way that the neural network will be actively reacting to its own ways being modified and to generate gibberish. Now, how to do that is when you're training, you're putting 2 different random binary IDs into the Hypernetwork. You generate 2 copies of the embedded network, and then you literally just take the average and train that average to predict the gibberish. This is a very elaborate training setup, and it's quite hard to balance because we have too many adversarial training going on. There are some tricks I'm going to show in a later slide. But to basically wrap up, our approach is connecting a lot of different dots here. We have first, you introduce a differentiable quality degradation during training to make the audio watermark robust against audio modifications. My next steps are fuse the audio generation network with the embedded network and internalize the unique ID to make it robust, not against audio modification, but against program modifications. And lastly, to make it even more secure against collusion, you can either use anti-collusion codes or anti-tamper training. And these are some implementation trips. They're getting quite detailed, so I'm going to skip this slide. So when you're training a network, there's also a question because we have a lot of different training objectives. You can always adjust the weights between the watermarking laws and the like audio quality laws. In the more extreme setup, where if you want to protect your network against a really, really strong noise, you can just ramp up the watermarking laws. But then by that point, you're not adding watermark to audio. You're literally just adding audio to watermarks. So if you make the watermark too strong, the audio quality is going to suffer. So the question here is, how good is good enough? How many bits out of like a total of B bits do we need to recover for the watermarking scheme to be, for protection to be strong enough? If you try to make the problem definition clear with a bit of mathematics, the better way to define it, out of total of n users to uniquely identify the user at a given confidence level, how many bits out of a total of n bits of B bits needs to be accurately recovered? So there is actually an analytic form to solve this. You basically break it down into cases when k out of B bits are actually recovered, and weight is going to end up with basically a weight of binomial distributions. So the results are here. If you have 128 bits for the watermark, we look at the cases where your plugin has 10,000 users, 100,000 users, and 1 million users. Look at the curves. So basically this means if you have more than like 85% of the bits accurately recovered, with a pretty good confidence level, you can say that who's actually, doing the bad things. And when you're looking at this confidence level, you want the confidence level to be really high, really close to 1, because you don't want to, put the blame on any innocent users. You definitely don't want to, make that happen. But here, the takeaway is for a watermark scheme with 128 bits, you only need you can tolerate 15% of the inaccuracies. Now, a different case, if you look at when you have like a lot of bits, like 1,000 bits in the watermark. Now, in this case, your watermarking system only needs to be performing barely better than random to be able to uniquely identify a malicious user. So to wrap up, why I'm doing this talk, and this is probably the first documented approach of designing an offline deployable, user-unique, and anti-tamper audio watermarking system. What I'm showing here is not published, it's not patented, and I have no intention of patenting or publishing in detail. The reason here is I want you to actually copy the methodology, but I don't want to copy how like the details. When we're designing a system against potentially malicious people and crackers, we want some diversity in approaches. We don't want everyone to design the same watermarking system, because if one of them get broke, everyone else will get it broke. So take this as an inspiration and design your own watermarking system. I guess the rest are questions. If you want to hear some samples, I'm also.
Thank you so much for the presentation. It's a really cool approach, especially the fusing. My question is about the recovery process, the accuracy of the recovery process. Am I correct to assume that in this slide, if I run the same input audio at least 10,000 times, there's a high chance that I might get a watermark that is not, like basically the watermark recovery will not be accurate, so I'll be able to get by the watermarking process. Is that correct?
There are two levels of inaccuracy we're talking about. One is your watermark has 128 bits. What if we only recover accurately 80 bits out of them? What if we recover 90 bits out of them? And the graph is showing that if you multiply 128 by 0.85, so maybe around 90 bits, if you recover 90 bits, you're pretty safe to say that you know who's generating that audio. But the other thing is, for that probability, how many chance you have to blame it on a completely innocent user. And that is what this graph is telling. And for that, you want the confidence level to be real low. And in this case, if you're like 85% for 1 million user, your confidence level is way below, is like 1 out of 10,000.
But does that not mean, because the system is probabilistic, that there is still like, it's not infeasible basically to get by the watermarking system? Is that correct? Like, I'm just trying to understand because of the probabilistic nature of the system, it is still possible to bypass it, right?
Yeah, I mean, if you're looking at the bypassing probability, this is not going to be this graph, but you're talking about the P-rec itself. So in extreme case, if you just add like a dB SNR 0, you know, like super strong noise, then everything will be gone. But so is the audio.
Okay, do we have another question?
It's not really a question. Great talk, thanks. I'd be curious to listen to the gibberish audio you get when you average the two networks from two different users. I'm curious in listening to that.
Yeah,
if you have it.
We have that sample here. So I'll first play the one that's just been converted without the model averaging. So this is the better example.
I've been waiting, I know you said would come to pass. I've been saying, I'm thanking you for your promise in advance.
So after averaging two models,
I've been saying, I'm thanking you for your promise in advance.
so it's like being filtered, you know. If you look at the spectrogram, like everything's being emphasized and there are like all kind of glitches. This room is a little bit reverberant, so it probably a bit different than that strong.
Okay. Great talk. Thanks very much, Kanru. Give him another round of applause.
Thank you.